Alright, in this lesson we're going to be talking about dot product, and we're going to define what that is and some properties, and we'll have a theorem about it. Alright, so first off we're going to let U be ABC and V be DEF. And the mathematical way to define a dot product is that U dot V is equal to AD plus BE plus CF. Sometimes this is called the scalar product because that's not a vector, that's a scalar. Okay, of course if you only had two components you'd only have the first two. There are some easily verified properties, but we won't go through verifying them, but you certainly could. Alright, so one is that U dot V is the same as V dot U. That, in order to prove this, it would be really easy. You just go back to the previous thing and have them defined as they are. And V dot U would be dA plus EB plus FC, and scalar multiplication is commutative, so you can reverse the order. Okay, another very important property. U dotted with itself, whoops, not V, U dotted with itself is equal to the magnitude of U squared. You can just see that would be A squared plus B squared plus C squared, and put it under the square root and you got magnitude. Alright, we also have the distributive property. U dotted with V plus W equals U dotted with V plus U dotted with W. That also works if you put the dot product on the other side of the parentheses and all that. For the zero vector dotted with any vector is 0, but not a vector, it's a scalar. And the last tells you about how scalar multiplication works. So if you have alpha times U dot V, where alpha is a scalar, that's the same thing as alpha U dotted with V, which is the same thing as U dotted with alpha V. So in other words, that scalar can move around in any way, shape, or form through that dot product however you want it to go. Alright, so we have a theorem. Okay, we're going to take two non-zero vectors. So let U and V be non-zero. You just heard my cat. Okay. If theta is the angle between U and V, then, alright, we have a formula. Cosine of theta equals U dot V. Yes, there's trig, rearing its ugly head. U dot V over the magnitude of U times the magnitude of V. Okay. Just a brief sort of interlude before we prove this. How are we going to prove it? I'm going to draw a triangle. And we always, those are, so A, B, and C there, capital A, B, and C would be the angles. And then the sides are opposite. That would be C, that would be B. And we know from the law of cosines that A squared is equal to B squared plus C squared minus 2BC cosine A. And that's how we're going to prove this theorem. Okay, so let me draw a picture that's relevant to this situation. So we have a vector U, and we have a vector V, and we have an angle theta between them, and we need to make a triangle. So we need that third side. Now we don't really know what that third side is, so let me call it question mark vector. But we do know from scalar addition that if I add U and question mark, I get V. So U plus V equals question mark, which means question mark is equal to, I'm sorry, I got that mixed up. U plus question mark equals V. So that means that question mark, if I just subtract u from both sides, would be v minus u. So that's what that side is. Now, to use the law of cosines, we can't just use vectors, we have to use magnitudes. They have to be scalars and distances. So, here's how we'll do it with this picture. So, we're going to use this angle theta as our angle. So, we've got the magnitude of v minus u squared equals the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine of theta. Alright, so that's just a easy first step application of the law of cosines. And then we go back to our property. So we're going to use property 2 and we're going to use property 3 eventually. And we'll use property 1. Okay, so we're going to break all the magnitudes except for these two guys over here. These are all magnitudes squared. So we're going to take that second property and go backwards. So this is going to be v minus u dotted with v minus u. And this is going to be u dotted with u and v dotted with v minus 2 magnitude of u magnitude of v cosine theta. This particular theorem that's proof, the way to derive it, it gets ugly before it gets clean. So since we have the distributive product property that works, we can FOIL out this. So we're going to get v dot v minus u dot v minus v dot, I always used to spell FOIL wrong. I spelled it F-I-O-L, but I still got the same answer, so I guess that's all that counts, right? And then we've got u dotted with u. Okay, and let me just copy the rest over. So we've got u dot u and v dot v. A little tedious just to have to copy this stuff. 2 magnitude of u times magnitude of v cosine theta. And then we have what I like to refer to as the cancel party. So you see the same thing on both sides, you can get rid of it. So we've got v dot v on both sides. We've got u dot u on both sides. So those are all going away. These two guys, using property 1, those are the same thing, because vector scalar dot product is commutative. So this is going to be minus 2 u dot v, that's what all that side simplifies to, and what's left on the other side, minus 2 magnitude of u magnitude of v cosine theta. And then if I just solve for cosine theta and divide by everything else, I get that cosine theta equals u dotted with v over the magnitude of u times the magnitude of v. Okay, and we have that relation. So we'll use that in our next video on dot product.